class, we are going to discuss one of the most important topic of electrostatics, and that is Gauss theorem. So before I start with the topic, it is very important to understand that why there is need to study Gauss theorem. Whatever we have studied till now in this chapter is that any isolated point charge serves as a source of electric field, and this electric field is denoted by the electric field lines. And we have also studied that the electric field lines associated with the positive point charge is always pointed in the outward direction, and the electric field lines associated with the negative charge always points inwards. But now the question arises, is there any way by which I can find the number of field lines associated with a given surface when I kept a charge inside it? Let us take an example. If I have a cube in which I have kept a charge q here, is there any way by which I can find the number of field lines associated with the whole surface due to that charge q? So here comes the role of Gauss theorem. This theorem relates the number of electric field lines with the charge kept inside that surface. So simply I can say that the Gauss theorem is a mean to relate the electric flux with the charge kept inside a surface. So let's continue with it. First, I'll discuss what exactly Gauss theorem is. Later on, I'll start with the proof of Gauss theorem and then some problems based on the Gauss theorem. So let's start. Now, before I start with the terms related to it, it is very important to understand that what is the meaning of the term electric flux. So let's start with it. Electric flux means the number of electric field lines passing from a unit surface area. Now, let's discuss it more simply without going into the terminology. So, this electric flux basically deals with the number of electric field lines. As we know that whenever we are discussing about a charge, an isolated charge is a source of electric field. And to denote this electric field, we basically use electric field lines. And simply we generally take that with a positive charge, the electric field lines is always pointed outwards, and with the negative charge, the electric field line associated with it is always pointed inward. Now, when I am saying that the electric flux is needed to be calculated, it means that what are the number of field lines that will cross that area, right? If I am saying that I have a charge with me, and let us say that charge is kept inside a football, so that football will act like a closed surface, and the charge I have kept there, it will result in the creation of field around it. It means when I am saying how many number of electric field lines are passing from that football, it will indicate that electric flux associated with that football. Similarly, if I have a cube, as you can see on the screen, if I have a cube with me, then if I'll kept a charge q inside it, then what are the number of field lines associated with the whole cube will determine the electric flux through the whole surface, right? And in order to find this flux, we have to understand some of the simple terms. This electric flux, right? This is simply calculated by the dot product of electric field vector and areal vector, right? Now you can see on the screen, this is a surface and the areal vector is always pointed outward. Remember, keep in mind, areal vector is always pointed normally with the surface. It means whatever the surface I have, the electric flux is calculated through the whole surface, and the areal vector will always be normal to it. Now let's take the example of this cube first. We know that a cube has 6 faces. It means I can draw 6 areal vectors linked with 6 different surfaces. Now as I can see on the screen, there are 3 surfaces in front of us. So now see, the flux associated with the surface which is upward, this will be pointed in this direction, that is upward, that is normal to it. The flux associated with the second surface will again be normal to it, and the flux associated with the third surface will be in this direction, right? Similarly, the flux which is associated from the surface lying at the bottom will be downward. The flux which is associated with the surface which lies in the backward direction will be outward, and it will be normal to it. So always keep in mind, whenever I am talking about areal vector, it will always be pointed in the outward direction. And if, let us say, if this is a surface which I have drawn here, and if this is the areal vector, and if the electric field is also in this direction, see, it's quite simple. Whole of the electric field lines will have to cross this area. But now the question arises, what will happen if the electric field is at a certain angle with the areal vector as shown in the figure? So in this case, we will take the dot product of E and A. And what basically this dot product denotes? It denotes that how many electric field lines are passing normally to that surface, right? Which simply result in the given definition, as you can read from the screen, the total number of electric lines of force passing normally through that area, right? So further I can write this as, this is E A cos theta, right? And this theta, it denotes the angle between electric field lines and the areal vector. I hope it is clear to you. Now let's move to the next topic, that is the proof of Gauss theorem. Now in the beginning of this video, I told you that this Gauss theorem relates flux with charge, right? So there will be a relation between this. Now this Gauss theorem states that the total electric flux passing through a unit area will be 1 upon epsilon naught times the total charge enclosed by that Gaussian surface. Now again, there are few terms which we need to understand before we start with the proof. The first term is, I use the term Gaussian surface. Now what exactly this Gaussian surface is? When I started this video, from the beginning I am saying that we are dealing with the flux associated with a closed surface. And this hypothetical closed surface is nothing but it is called as the Gaussian surface, right? So whenever we are trying to find the flux, what we have to consider, we have to first consider a hypothetical surface which will be closed in nature, and that will be called as Gaussian surface. Now this electric flux, according to Gauss theorem, this will be equal to 1 upon epsilon naught times the total charge enclosed by that Gaussian surface. Now understand the meaning of this thing. What is the meaning of charge enclosed? Let us say if I have a closed surface and if I have kept a charge which is plus q, then according to Gauss theorem, the flux associated with it simply can be written as q by epsilon naught, right? But what if I'll say that there are two charges lying outside the surface, 2q and 3q, right? See, these two charges, that is 2q and 3q, they do not lie inside the Gaussian surface, and that's why we will not consider these two charges. It means this Gauss theorem tells that the flux, that is electric flux, will simply be related with the charge kept inside that Gaussian surface. And by using this theorem, we can find the flux through the Gaussian surface due to a charge q which is kept inside that, right? Now simply let's start with the proof. Now in order to start with the proof, first we have to consider a Gaussian surface. As you can see on the screen, I have taken a charge plus q here, and I have considered a hypothetical Gaussian surface which is spherical in nature. Now try to understand it. If I have a Gaussian surface which is spherical in shape, due to a charge q, I have to find the flux. Now, what will happen if I am drawing a simple, let us say this is the small surface, right? Let's write it with ds. Now, if this is a very small surface, definitely there will be some of the electric field lines that will cross this surface, right? Now let us, I am simply saying that there are two lines passing from this surface, right? And if I'll divide this whole sphere into 100 such small parts, I'm again repeating, if I'm dividing this whole surface into 100 such parts, then if I'm saying that the flux or the number of field lines passing from one small such surface is 2, then you can simply say that the total number of field lines passing from the 100 surfaces will be 2 into 100, that will be 200, right? The flux associated with a small surface can be obtained by the dot product of electric field vector and areal vector. Now you can see from the diagram that this is the electric field vector and this is a small element. Let's write it with ds. It's very small surface. So now what will be the flux associated with this small surface? Can I write it like this? E dot ds, right? This is a flux associated with such small surface. That's why I can write it as d phi. This is a small flux associated with this small surface. Now if I need to find the flux associated with the whole surface, so what I can do here is I can integrate this small flux, right? And if I'll integrate it, what I'll get the integration of E dot ds. Now this term simply denotes the dot product of two vectors. Now I hope that all of you know how we get the dot products, right? Still I am just explaining it in brief. If I have two vectors a and b, and if I need to find their dot product, then simply it is nothing but a b cos theta, and this theta is the angle between the two vectors a and b, right? Now similarly what I need to do here is, can I write it as integration e ds cos theta. Now let's understand few basic terms. See, as I told you that it is a closed surface integral. Again I am repeating, it is a closed surface integral. Since it is closed surface integral, I have to mark the sign of integral like this, since it is associated with a closed surface, right? Again I'll put it here like this. And now what is this angle theta? This theta is the angle between electric field vector and areal vector ds, right? Now simply you can see from the figure what is the angle between E and ds. This angle is simply nothing but 0 degree. Now if this angle is 0 degree, what I can write here that this phi can be obtained by the closed surface integral, and it will become EDS cos 0. And we know that this cos 0 is simply 1. So what I can write here is that the flux which I'll get from here, this will be E ds and the closed integral along it, right? Now you just have to think that if I have considered this Gaussian surface as spherical, if I'll integrate, means if I'll combine all the small elements ds, what I'll get the whole surface right? And that is why the integral of ds can be obtained by the surface area of sphere, right? But before I integrate it, what you simply need to understand is, see, I have this flux as closed integral of E ds. Now see, this E is a constant term. Now let's understand why this electric field is a constant term. See, we know that the electric field, it can simply be obtained in terms of magnitude like this. It is 1 by 4 pi epsilon naught q by r square. Now check this figure again. Can you see here that for all the points which lies on the surface, the distance of this charge from the surface is nothing but r. For all the points lying on the surface, it is r. Whether it is here, here, or it is here. For all the point, it is r, right? And we have the same charge associated, that is q. So now check this term again. 1 by 4 pi epsilon naught, it is a constant term. Q is constant. R, for all the points lying on the surface, R is same. So what I can say here is that this E is a constant term. So I can take it out from the symbol of integration. Now it will become E, and the closed integral of ds, this will be the flux associated. Now, as I just told you that the integral of ds, it will be the surface area of sphere. And why this is? Again check. If I'll integrate, means if I'll combine all such small elements, I'll get the whole surface. And for such small surface, this will be phi. This is equal to E. And what I can write here? I can write here 4 pi r square. Now, if I'll put this value of E here, so what I'll get? This phi will become 1 by 4 pi epsilon naught q by r square. This is the value of E which I have substituted. Now, again, see this whole term, right? So it will become 4 pi r square. Now on simplifying, what we'll get, see this 4 pi will get cancelled, this r square, it will also get cancelled, and what we are left at the end is this. So we got the final result as this phi is q by epsilon naught. So in today's video, we have discussed what exactly Gauss theorem is. We have continued with the proof of Gauss theorem, and in the next class, we will start some of the problems which are based on Gauss theorem. Till then, revise the topic. Have a nice day.